So in the last video, we established that for uniform circular motion, the acceleration always points towards the center. Now we know from in linear motion that the net force is always in the same direction as the acceleration. So the question is this the same case for circular? So in circular motion, is the net force also in the same direction? Can we apply Newton's second law? And before we get into two examples to demonstrate that, let's talk about these two terms. Radial acceleration and centripetal acceleration. I briefly mentioned that one in the last video, but I just want to specify what it is. First thing, know that radial and centripetal, these are the same thing. So we're talking about the same thing. I typically use centripetal, but occasionally I'll go back and say radial. And you may be reading something and it'll say the radial acceleration. So no, these are the same thing. And what it is it's that acceleration towards the center in circular motion. So when you have circular motion, this is either called the radial or the centripetal acceleration. So we write an A with little r or A with little c. This is the one I typically use, but you can use this one as well. It's called radial because it's along the radius of the circle, because it always points in. So this is on the radius. It seems redundant to write it, but there you go. Centripetal, the word centripetal means center seeking. So you can see why they would call it such. So it's an acceleration seeking the center. So the question is, since we have this radial or centripetal acceleration, will we also have a net force in the same direction? So let's look at two examples. One, you're holding a rope tied to a bucket, spinning it in a circle. And so what we want to do is analyze the forces. Now we know that the acceleration is going to be right along in this direction, towards the center of the circle, not up here. It's towards, since the motion is in this direction, it's towards the center of the circle. So what we can do is we can draw this again, if you imagine it from the top. So if we were looking straight down on this, what we would see is the object is moving around in a circle like this. And so that acceleration is straight towards the center. So that's what we're doing. Okay, to do this, what we're going to do is do a force diagram from the side. So we're going to do side view. And we're going to do a force diagram. So we'll say the bucket is a sphere. Then you're going to have some tension pulling up like this. That's the rope. And then, of course, you have the force of gravity. And so the question is the net force in this direction, towards the center? Because that's my centripetal acceleration. And so if we did our components, we would do t in the x, and then t in the y. And this is actually t in the radial, but whatever. And what you'll see is this one and this one cancel out, which leaves only tx. So yes, the net force is in the same direction as the acceleration, the centripetal acceleration. Okay, let's look at another one. So this one, we're actually looking down onto a table, and there's a metal ring, and then this ball is rolling around inside of the ring. And we want to know, is the net force, we know the acceleration is this way at this point, but keep in mind that, if the ball's up here, the acceleration is this way. It's always towards the center, so it's always changing. Is the net force also inward? And so what we want to do is do a side view to analyze the forces. And so if I think, so if this was on a table, you kind of squat down and you're looking at it from this direction. What we would see is, well, the ball is sitting on a table, so you have a normal force pushing up. Normal force, and then you have the force of gravity. And then we have the force of the ring on the ball, and that's pushing it this way. That's what's making it turn. And so we get, it's actually a normal force off the wall, but we'll just say the force of the ring acting in. So here we can see, yes, again, the net force is in the same direction. as the centripetal acceleration. So that leads us to a conclusion that for circular motion, for uniform circular motion, again, uniform means same speed, the net force is center seeking. Seeking, which is the same as same direction as the acceleration. And we would call that centripetal or radial. And in fact, we can apply Newton's second law. The centripetal acceleration is going to be the net force divided by the mass. So we can get the centripetal acceleration. And that's just a qualitative. We'll come back to all of this, but just qualitatively being able to figure out what is the force causing the acceleration. And the force is always in the same direction, so we could write it in here. This is the net force. Over here, the net force, and so on.